grown accustomed to miracles. We have become used to the mysterious but familiar force of electricity. Yet, during the past 100 years, we have acquired such capability through electricity as to alter the whole of life. We reach outward into the universe. We look inward into ourselves, enlarging our own capacities. At base, there is power. Power to drive, power to command. Power illuminates our world so as to make all ages that went before look like dark ones. And the electrical and electronics engineers have shown the way, for it is they who have discovered how to use and control electricity, this miracle force. One basic function of many engineers is creative design. They must blend an expert knowledge of what is possible with a sharp sense of what is wanted. In Charlotte, North Carolina, K.P. Lau designs power systems. His job is to give people what they need when they need it. This means knowing a great deal about human behavior.
The constant availability of electricity is what the general public expect. In the morning, when everybody gets up at the same time, they start using electricity. And in the evening, everybody cook at the same time. And during the noontime, everybody uses air conditioning at the same time. The demand of electricity goes way up. The operators here do have to know the system. Based on their experience with the various usage pattern, they can know when the high demand going to come up. We have enjoyed so much adequate, reliable service and depend on it almost to the degree that it's a necessity. Our challenge is to meet the peak requirement of the general public. When they flick the switch, they expect the light to come on. But the true story is there was so much generation, transmission, and distribution involved to provide the power to the customer.
Steve, it looks like this temperature is going to go up a little bit more than we expected today. So as the need of the steam units that we plan to take off tonight, just go ahead and take off a little bit earlier. As your load drops off, just go ahead and take them down.
In the 1920s, the power started to be used to light houses. Before then, it's mostly for the mills, for the industrial use. And then 1930s, we start using for irons, refrigerators, ranges, water heaters. And then to 50s, all of a sudden, vacuum cleaners and air conditioners. And then 60s, TVs. We just can't do without electricity nowadays. And engineer has the responsibility to educate the public about the complexity of the electricity generation. Engineers were trained to serve. Engineers are trained to work as a team. We have to build enough to keep up with anticipated growth, or we all have to look at the ways to be more efficient in how we use our energy. We have a project going on that stores electricity in a central location. And if it is successful, we could eventually have every household install some sort of battery so they can utilize those electricity from the battery during the peaking hour. feel very much at home here. I'm part of the design team that designed the switchyard. It's 5 years of my life.
Yet, KP knows his design is part of something far larger. In the end, he and his team feel a deep satisfaction over what they've achieved and over the miracle that electrical engineers have accomplished everywhere.
In the United States, the whole country is actually tied up as one grid. The generation, transmission, and distribution of electricity, in my opinion, is probably the all-time achievement of mankind. Everything we do, we touch, has to use electricity. And engineers are the people that put out those ideas and concepts to use.
It's a basic characteristic of engineers to like what they do. After all, people go into this kind of work because they enjoy solving problems, turning up the new and the wonderful. Debbie Candelora in Homedale, New Jersey, feels a personal involvement in what she does.
I developed optical fiber transmission systems that are used for long-distance telephone communications.
A key factor in developing new methods is that the work will contain many, many challenges.
I like to solve problems, I like technical work, but I'm a practical person. Rather than become a scientist and work in the research area, which does sort of the same kind of work, I wanted to do something that had immediate application. And that's where engineering comes in. You work with the technology, but you develop products that are actually used.
A basic role of the electrical and electronics engineer is to bring the miracles of modern science to the public. Fiber optics are a good example, for they have moved out of the lab and into everyday life, where once a wire could transmit only a single electrical signal at a time. Now glass can be processed to transmit as many as 250,000 signals, all at once, by means of light.
What we do is we send telephone signals, a voice channel. You pick up the phone and call your mother, but we send the signals by using light. Now, what we do is take a light source, in this case it's a laser, and we code the signal just like you would in Morse code, and use the light, flash it on and off basically to send this coded signal to the other city. But we don't just send the light through the air. In order to guide the light and make sure it gets where we want it to go, we use optical fibers.
One great thing about optical fiber is its versatility. Use is not confined to voice messages. Any signal will do. So the possibilities are just about endless.
What a fiber is a strand of glass, just like your window pane, only in a form that looks like a wire. But it's very, very pure glass. And its function is to take these light pulses and guide them from one location to another, around corners or through underground ducts down in manholes. And then at the far end, we receive the light, convert it back to an electrical signal, uncode it, and then convert it back into an audible signal. Lightwave's already gotten into the television industry. For example, the 1984 Summer Olympics in Los Angeles, the television coverage for that event was entirely over fiber optics.
For an electrical engineer like Debbie, the exciting thing is what may be done with light.
Right now you have a pair of copper wires coming into your house. Some people are saying that in the future that will be replaced by a pair of glass fibers. This will allow you to have a variety of services, such as cable TV or two-way video. You can bank at home, shop at home, that sort of thing, or connect your personal computer to some central computer. As far as people are concerned, the messages are very different. As far as the fiber is concerned, because of the coding we do, everything is just a series of light pulses. Whether it's computers talking or a video signal or people talking, it's just a string of light pulses.
And there always remains the very agreeable element of mystery.
Electricity, as well as light, are things that I use in my job every day. I know how they react. I can make them do things, but it's not something I could define. They still have an air of mysteriousness about them.
When a space shuttle, or orbiter, as some people call it, goes aloft, it's not just a matter of lifting off according to plan. For every device, there has to be a backup. That's where the imagination of engineers goes to work. Most of us by now are used to the image of men in space. What few of us think about, or even know about, is the endless checking and double-checking, testing and retesting that must stand behind every public event. Like the work being done by Mark Schmalz at the Space Center in Houston, Texas.
The Electronic Systems Test Laboratory is a engineering performance evaluation of the various communication subsystems that are on board the orbiter. This is really the only facility in existence that can test these components end to end, from the time the voice and the data goes in to the time it's supposed to come out here on the ground for the user. The interfacing in the actual end-to-end system may or may not work right. It's not unlike building a car in different parts of the country and then hoping the starter turns over when you hit the key. This is the kind of compatibility problems that you can run into, as well as testing it in actual flight conditions, which we can do here to see if there is a problem, either engineering-wise or operationally. If you practice it enough, then it becomes second nature, and there's no problem when the real mission comes.
How will small antennae perform beneath the tiles of the heat shield when their angle changes radically in flight? Engineers try every angle again and again.
Practice makes perfect. As far as the training of the people with the equipment here in the laboratory, as we're doing now for the next mission, is you can actually throw a monkey wrench in there and see how people react, just to see if the rest of the system reacts the way they should in a timely fashion. And quite often you can hone up on your operational skills so that when a mission like Space Lab or Solar Max comes along, everybody says, oh yeah, we've done that before and that's no big deal, we'll set up for it. And when the real mission comes, it's like another big sim.
Test. 1, 2, 3, 4. How do you read?
Before a mission goes up, there are thousands and thousands of man-hours spent in simulation of flight. On the ground, faults can be discovered and remedied, backups devised and installed. In space, a failure of communication is more than a minor problem. It can be a fatal danger. So when it's time for the real stuff, time for flight to begin, the people going up there know they can move with confidence. And all the way, astronaut, scientist, and engineer are in partnership, learning together. For this is truly a new frontier.
Roger, Bruce, loud and clear. Okay, Roger, copy that, Bruce.
Usually the scientific community that we deal with more on a theoretical basis will give us some kind of idea of prediction-wise, theoretically, how all this should work. But quite honestly, there's never been a real working system built to test their philosophies. And quite often we end up testing something and coming up with either something doesn't look right or doesn't look like they said it should. And a lot of times you end up rewriting the theory more than you do the hardware, because it's awful hard to rebut the hardware operating the way it does. Returning from space at Mach 25 is something that nobody on the ground could simulate.
One glance beneath the skin of a space shuttle will give a clue to the job of the electronics engineer. There's a great complexity in this advanced technology. Each vehicle is a working airship, designed and built for reliable and repeated flight. They must turn space into a theater for true experiment. Again, staged by engineers. Again, flexible and inventive.
Insulation piles on the orbiter is one example of an incredible jump in technology that allowed the heat dissipation of re-entry on the orbiter to be taken care of, but its possibilities and potential for use in the everyday life is considerable. I saw a demonstration once where a gentleman held a block of tile in his hand, poured liquid nitrogen at minus 320 degrees in one side and heated it with a torch on the other, and he was holding it with his fingers. Okay, just imagine what that would be like if you could heat it with a candle, the calculations say at least, if you didn't open the door. I believe in progress, and I always have. I feel that the space program has captured the imagination of the people since very early on with Kennedy and the push for the moon race. I think it sets people thinking. I think it sets them dreaming. You can be a part of it, and you can see it happen, and the dreams are not that. They can be reality.
Houston now, controlling control tower, rolling over confirmed.
Another basic characteristic shared by most engineers is that they are practical. After all, they have to be, for it is their task to bring flights of theory down to earth. Try asking an engineer what a computer is. Harvey Freeman in Minneapolis will tell you what it can do for you.
A computer is a device that, in a logical fashion, manipulates numbers or moves pieces of information around much faster than a human can. Today, in types of computers that we have controlled by a single chip, a single microprocessor chip. More computing power now on my desk than I had 10 years ago when I worked in a large company. The computing power is available to everybody, and no one ever had that before. The thrust is to make the systems easier to use, and one way of making these systems easier to use is make the communication easier to use. In order to be adaptable, you have to draw the computer to man. You have to put the computer in the particular environment it's going to operate in and not the other way around. That, I think, is the key to its success. The person should be able to use the computer without understanding it. It should be a resource just like the telephone is. When you use the telephone, you do not think of how the signal is being converted from one type of form, energy, to another type. You just know that when you punch a few buttons, you're able to talk to the person that you want to talk to. The computers and the network should provide the same type of service. A network is a collection of computers that can communicate with each other. There are different types of networks, local networks, within a building or a room or campus environment. From there are people developing citywide networks that allow computers, networks to be connected together within a city. And then from there, geographically distributed networks, and there are a number of those that allow communication through microwaves or landlines or satellite links to have messages sent all over the world. The biggest breakthrough that I think is coming along would be in the replacement of the various types of systems we have now into, say, a single type of system, a single type of communication mechanisms. Maybe fiber optics is the answer. Maybe the very, very large integrated circuit chips in combination with that. Knowing what is coming on and seeing what people are doing makes it exciting, and then some months later or years later you read about it in Time or Newsweek or in the trade press and you say, oh, well, I was doing that a year or two ago.
The key to the computer revolution is the chip, and the key to the chip is miniaturization. What used to occupy a great deal of space is now reduced and concentrated into a tiny space containing thousands of circuits. Instead of a web of many connections, laboriously soldered by hand, there's a whole pattern printed. We move from things hand-built to things mass-produced. For engineers, the labor and the cost lie in design and testing. Once that is done, smaller means cheaper, and smaller means far more reliable.
Now, everyone has the ability to control what they want to do with the computer and use the computer and not have really to go to someone else for permission to access resources for their daily tasks. What the engineers are doing is supplying the canvas, the things that ties all the colors together. They're supplying the building blocks and the mechanisms that allow them to work together in some type of synergistic fashion in order to handle any particular environment or application.
Basically, engineers move from the special case to the general application. In Palo Alto, California, teams are working to assist handicapped people who need help. Larry Leifer, a biomedical engineer, believes that everybody will benefit from what is being learned.
The methods being developed now to do basic research on nerve and muscle function, coming largely from the engineering community, are having a profound effect on physiology and medicine. We don't challenge the physiology. We take the individual and their state of function as a given. We then try to assess what they can do, and we try to come up with engineered solutions to increasing their functionality. In almost all cases, we use the computers. They are not something we're doing research on. The one that's perhaps been most visible is a manipulation aid, based on a hypothesis that industrial robots, manipulators, can provide useful services to a person with severe physical disability. That individual in our environment is usually a spinal cord injured individual with a neck level injury leaving them paralyzed in all four limbs.
Faster.
Faster to 160 steps.
Left.
Left. Good hard.
Continuous.
Continuous.
Right.
Any robot should have a human interface. You should be able to tell it what to do.
Stop.
Tell it when to start
Down.
and when to stop. Philosophically, it's saying, let's make robotics technology accessible to everyone.
Reverse. Stop.
It's actually a precursor to the domestic servant robot that I think will be in your future. It's going to be several years away, 15, 20, but it will ultimately be as common as an automobile. I'd want to keep it clear that we're not saying that these machines should replace people's relationship to other people. They should replace some of the nagging little constant chores that have to be done by an individual. If I need to scratch my eyebrow, I did it. It was quick. It was easy. If I were a quadriplegic, I'd have to ask you to do it. We've gotten involved with vision, and in particular low vision. We focused on developing a handheld camera, a camera that would convert printed text into a computer-readable sequence. We have to know more about the human machine, how it works, how it thinks. That's part of the challenge that we have in rehabilitation. We can compare what a computational model says and what a body says. And our task is to make the two come together. That is a precursor to going back to those muscles and controlling them externally so that we can produce the same pattern of activity to create movement, to create walking using residual muscles. Curiously, in the beginning of our center's existence, there was a little mandate that said, "Thou shalt not work on wheelchairs." And that came from the impression that I had not worked with them, but that people had, lots of people had, and there hadn't been any breakthroughs. So we pursued non-contact. We chose ultrasonic range finding as the mechanism to monitor the position of the head of the driver. The driver tilts the head forward, the vehicle goes forward, back it stops, right it turns right. It works elegantly. It's a machine that adapts to the user. The engineering community has inherited the challenge to perform the miracle of making that life a fully functional and satisfying life based on the use of technology that assists them. We have a very big challenge out there in front of us.
The challenge is expanding and accelerating in a way that can only be called explosive. The number of new achievements is piling up so fast that there's no room left to be astonished. Throughout the brief span of civilization, our progress has been based upon adaptability. And this is the true contribution of the electrical and electronics engineers. Not only have they produced miracles, they have shown us how to use them.